On July 14th, 2015, a spacecraft the size of a grand piano flew past a frozen world 3 billion miles from the sun, and for 9 minutes, humanity got its first real look at Pluto. What NASA's New Horizons sent back stunned everyone. Towering mountains of water ice, smooth plains of frozen nitrogen the size of Texas, and wrapped around the entire planet, a thin, glowing blue. Haze rising nearly 300 kilometers into the black. But buried inside that beautiful data was a number that didn't make sense. A number NASA scientists have spent the better part of a decade trying to explain. Pluto's atmosphere was cold, far colder than physics said it should be. And for almost 10 years, nobody could tell you why. Until now. Stay with me, because the James Webb Space Telescope just closed the book on one of the strangest unsolved mysteries in our solar system. And the real answer is stranger than most of the theories that tried to explain it. Let's go back to that flyby, because you need to understand exactly how strange this anomaly was. When New Horizons swept past it, Pluto. In July 2015, scientists had a working model of what its atmosphere should look like. Pluto's thin shell of nitrogen and methane gas should have settled at a temperature around negative 173 degrees Celsius, based on standard atmospheric physics. The same equations that accurately predict conditions on Mars, Titan, and virtually every other atmosphere we've measured. Instead, the real temperature came back over 30 degrees colder than the models allowed for. In planetary science, that's not a rounding error. That's a full-blown anomaly, the kind that makes researchers go back and recheck their instruments, recalibrate their sensors, and rerun the math from scratch, which is exactly what they did, multiple times, and the discrepancy refused to close. Something was pulling extra heat out of Pluto's sky, and standard atmospheric gas physics simply couldn't account for where that energy was going. For a small, distant world that most people had already mentally filed away as a dead, frozen rock, this was a genuinely big deal. Pluto orbits the Sun once every 248 years, at an average distance of about 5.9 billion kilometers, meaning it receives roughly 900 times less sunlight than Earth does. By all logic, it should be a simple, quiet, thermally boring place. Instead, its atmosphere was behaving like something was actively managing its temperature, radiating away energy at a rate its chemistry couldn't obviously support. And that thin blue haze photographed by New Horizons, the same haze that made the mission's images so hauntingly beautiful, sat right at the center of the mystery. It wasn't dense, it wasn't dramatic to look at, but it layered itself into delicate, glowing bands stacked on top of each other, visible proof that something complex was happening in Pluto's upper atmosphere that nobody yet understood. Then, in 2017, a planetary scientist named Xi Zhang at the University of California, Santa Cruz, proposed an idea that most of his colleagues initially dismissed as, frankly, a stretch. Zhang suggested that Pluto's haze wasn't just a passive layer of dust and ice drifting in the wind. He proposed it was doing something active, something that, at the time, went against nearly everything planetary scientists believed about how atmospheres regulate their own temperature. His theory was this: those microscopic haze particles could absorb ultraviolet light streaming in from the distant sun, and instead of simply warming up like a rock sitting in sunlight, they would re-emit that energy specifically as mid-infrared radiation, essentially converting incoming light directly into outgoing heat, and doing it far more efficiently than ordinary atmospheric gases ever could. In other words, Zhang was arguing that solid particles, not gases, were quietly running Pluto's thermostat. For decades, the accepted science said gases controlled planetary climate. Carbon dioxide drives Venus's runaway greenhouse effect. Methane shapes the thick, orange skies of Titan. Zhang was suggesting Pluto played by a completely different rulebook, one where haze particles themselves acted as the planet's primary cooling mechanism. Most of the scientific community treated this as an interesting but unproven hypothesis, and for good reason. There was no way in 2017 to actually test it. Zhang's model made one very specific, very testable prediction, though. If his theory held up, Pluto's haze should emit a distinct, measurable glow in the mid-infrared spectrum, a signal so faint that no telescope operating at the time had the sensitivity to detect it. Not Hubble, not any ground-based observatory. The technology simply didn't exist yet to catch a signal that faint, coming from a world that small, that far away. So Zhang's prediction sat there, unconfirmed, for 6 years. A theory waiting for an instrument that hadn't been built. That instrument arrived in December 2021, when the James Webb Space Telescope launched from French Guiana and began science operations the following summer. Webb wasn't built with Pluto as a primary target. Its main mission focused on the deepest, oldest galaxies in the universe. But its mid-infrared instrument, MIRI, happened to be exactly the tool Zhang's 6-year-old prediction required. And in May 2023, an international research team led by Tanguy Bertrand finally pointed Webb directly at Pluto and its largest moon, Charon, to find out once and for all whether that decade-old temperature anomaly finally had an answer. Here's what makes this observation genuinely difficult and why it took until May 2023 to even attempt it. Pluto and Charon are locked in a mutual orbital dance, and from Earth's perspective, they sit so close together that separating their individual heat signatures had never been possible with any previous telescope. Charon is roughly half Pluto's size, close enough and bright enough in infrared that its glow had always bled into any measurement of Pluto itself, muddying the data. Webb's precision changed that. For the first time in the history of astronomy, Bertrand's team was able to cleanly separate the infrared signatures of the two worlds, isolating Pluto's atmospheric glow from its moon's surface heat with a level of clarity no observatory had ever achieved. Using MIRI, the team scanned Pluto across 4 specific infrared wavelengths, 15, 18, 21, and 25 microns, each one chosen because it corresponds to the exact kind of emission Zhang's 2017 model had predicted, and the results, when they came back, were unambiguous. Pluto's infrared glow was significantly stronger than a simple frozen surface could account for on its own. Something above that surface, in the atmosphere itself, was actively radiating extra heat out into space. When the researchers subtracted Charon's contribution and isolated Pluto's atmospheric signal in complete isolation, the spectral lines lined up almost perfectly with what Zhang had predicted 6 years earlier, sitting in a paper most of the field had quietly set aside. The haze wasn't simply scattering sunlight the way scientists had always assumed. It was glowing, actively converting incoming solar energy into outgoing infrared radiation, functioning almost like an exhale, a planetary mechanism nobody outside of Zhang's small camp had taken seriously. NASA finally had its missing energy. The 30-degree gap between the predicted and measured temperature of Pluto's atmosphere, the anomaly that had sat unresolved since 2015, had a real, confirmed physical explanation. The haze wasn't a passive byproduct of Pluto's chemistry, it was the driving cause of its extreme cold. And that finding rewrote a basic assumption planetary scientists had carried for decades, the idea that gases alone control the planet's climate. On Pluto, solid microscopic particles, compounds called tholins, were doing the real work. So what exactly are tholins, and why does this matter beyond one small distant world? Tholins form through a fairly elegant chemical process. Ultraviolet light from the sun strikes methane molecules in Pluto's thin atmosphere, triggering a cascade of chemical reactions that build increasingly complex hydrocarbon compounds, the same basic organic chemistry that gives Titan its famous orange haze and gives comets their reddish-brown tint. As these tholin particles form, they slowly drift downward. Through Pluto's atmosphere, layering into the delicate, glowing bands New Horizons photographed back in 2015, each layer radiating infrared heat as it sinks, cooling the atmosphere from the top down in a continuous, ongoing cycle. The entire system functions almost like a slow, self-sustaining engine. Haze forms high in the atmosphere, radiates heat away, drifts downward, and eventually settles, repeating with every single orbit Pluto makes around the Sun. A 248-year cycle most of us will never live long enough to see complete even once. And Webb's data revealed something else, a detail that connects Pluto directly to its largest moon in a way nobody had fully appreciated before. Some of the methane in Pluto's atmosphere doesn't stay in Pluto's atmosphere. It slowly leaks into space and drifts across the gap toward Charon, where sunlight transforms it into the same reddish organic compounds visible on Charon's north pole, a feature scientists have nicknamed Mordor because of its dark, rust-colored appearance. In a very real sense, Pluto is slowly painting its own moon, one methane molecule at a time, a process happening right now as you watch this. Once Bertrand's team confirmed the mechanism on Pluto, the obvious next question became, is this happening anywhere else? The first and most natural place to check was Titan, Saturn's largest moon, already famous for its thick, orange, methane-rich atmosphere and its eerily Earth-like lakes of liquid ethane. Webb turned its instruments toward Titan's limb, the thin edge of its atmosphere silhouetted against space, and found something strikingly familiar. The same mid-infrared wavelengths detected glowing on Pluto appeared again on Titan, and in some measurements, even more strongly. Titan's much thicker atmosphere appeared to be radiating away energy through a remarkably similar haze-driven process, suggesting this wasn't a one-off quirk unique to Pluto, but potentially a shared mechanism across multiple hazy, methane-rich worlds in the outer solar system. Researchers studying the data began referring to Pluto and Titan informally as mirror worlds, two frozen bodies, separated by roughly 1.3 billion kilometers, both wrapped in organic haze, both apparently governed by the same underlying tholin chemistry regulating their skies. And when scientists turned Webb toward Triton, Neptune's largest moon, a world long assumed to be geologically inactive and thermally unremarkable, they picked up faint atmospheric heat signatures, hinting that its own thin. Nitrogen haze might be operating under a similar principle. 3 separate icy worlds, 3 independent confirmations of the same basic physics, quietly rewriting what scientists thought they understood about how cold, distant atmospheres actually behave. This is the part of the story that deserves real attention because it reframes what Pluto actually represents. It's not a dead, frozen curiosity sitting at the edge of the solar system. It may be the first confirmed example of a genuinely new category of atmospheric physics, one where solid organic particles, not gases, do the heavy lifting of regulating a planet's climate. And if it's happening on 3 different worlds in our own solar system, the next question researchers immediately began asking is whether this same mechanism might be operating on planets we haven't even visited, worlds orbiting other stars entirely. Now let's talk about why any of this matters beyond satisfying curiosity about a small, frozen world most of us will never visit. Because the Deeper Webb's team dug into Pluto's haze chemistry, the more they realized they weren't just looking at a cooling mechanism. They were looking at a chemistry set that might connect directly to one of the biggest questions in all of science. How does life actually begin? Those tholin particles driving Pluto's atmospheric cooling aren't simple. When researchers studying Pluto's surface and near-subsurface material analyzed the composition of these compounds in detail, published research in the journal, Astrobiology laid out the case plainly. Tholins are complex, macromolecular organic solids, essentially networks of aromatic structures connected by chains of carbon and hydrogen, and laboratory experiments recreating Pluto-like conditions have shown that similar starting materials, when frozen in water and ammonia ice and exposed to the right energy sources, can produce nucleobases, the actual molecular building blocks of DNA and RNA, including guanine, one of the 4 core letters of life's genetic code. To be absolutely clear, this does not mean life exists on Pluto. Nobody studying this data is claiming that. What it means is that the same basic chemistry capable of producing life's fundamental ingredients appears to be happening. Naturally, right now, in the atmosphere and surface ice of the coldest, most distant world we've ever photographed up close. Zhang, the scientist whose 2017 theory started this entire chain of discovery, put it simply once Webb's data confirmed his prediction. He said the team was proud because the observation confirmed exactly what the model had forecast 6 years earlier. And he pointed out something that reframes the whole story. Pluto isn't an outlier sitting alone at the edge of the solar system. It sits in a genuinely unique position in the range of how planetary atmospheres behave, and understanding it gives scientists a template for understanding haze physics in extreme cold environments more broadly. Neptune's moon Triton and Saturn's moon Titan, Zhang noted, both carry similar nitrogen and hydrocarbon atmospheres, thick with haze particles, meaning whatever physical process Webb just confirmed on Pluto likely isn't a one-off. It's potentially a shared mechanism operating across multiple worlds in the outer solar system, each one a separate ongoing experiment in the same basic photochemistry. Here's a detail that deserves its own moment because it's easy to breeze past. Webb's observations showed that methane escaping from Pluto's thin atmosphere doesn't just vanish into space. Some of it drifts across the roughly 9,600 kilometers separating Pluto from Charon and lands on the moon's surface, where sunlight converts it into the same dark reddish compounds visible at Charon's North Pole, a region informally nicknamed Mordor by the New Horizons science team because of its rusty alien coloring. Pluto is, quite literally, slowly painting its own moon through an ongoing exchange of atmospheric material, a process happening continuously that Webb only recently gave us the tools to actually observe and quantify in detail. So where does the official research stand as of today? The primary findings were formally published in Nature Astronomy in 2025 under the title Evidence of Haze Control of Pluto's Atmospheric Heat Balance from JWST/MIRI Thermal Light Curves, led by Tanguy Bertrand of the Observatoire de Paris, with contributions from a wide international team including Emmanuel Lelouch and Panayotis Lavas. A companion paper detailing Pluto's atmospheric gas and haze composition from the same MIRI spectroscopy data was also published, confirming that Pluto's mid-infrared spectrum is a genuine mixture of reflected sunlight, gas emission, and haze emission working together, with the haze component confirmed as a significant, previously underestimated contributor to how the planet loses heat. This is real, peer-reviewed, published science, not speculation dressed up as fact, and it represents something genuinely rare. In modern astronomy, a specific theoretical prediction, made 6 years before the technology existed to test it, confirmed almost exactly as originally proposed. Think about what that timeline actually represents. In 2015, New Horizons handed us a mystery with no clear answer. In 2017, one scientist proposed an explanation most of his peers weren't ready to accept. And it took until 2023, in formal publication, in 2025 for the right instrument to finally exist, be pointed at the right target, and confirm what he'd suspected all along. That's not a conspiracy. That's not a cover-up. That's science working exactly the way it's supposed to, slowly, carefully, and honestly, even when the honest answer takes the better part of a decade to arrive. But here's what should genuinely excite you, because this story is far from finished. If haze particles can regulate atmospheric temperature this precisely on Pluto, Titan, and potentially Triton, then researchers studying exoplanet atmospheres now have a completely new variable to factor into their models. For years, scientists modeling whether a distant world could support stable, life-friendly conditions focused almost entirely on gases, greenhouse effects, and distance from a host star. Pluto's confirmed haze mechanism suggests atmospheric particles themselves might play a far larger role in stabilizing a planet's climate than anyone previously accounted for, a factor that could apply just as easily to a rocky exoplanet orbiting a distant red dwarf as it does to a small, icy world at the edge of our own solar system. And that reframing is exactly what's driving the next wave of research, because scientists studying Pluto's haze aren't done. New observation campaigns are already planned to track how the haze changes as Pluto continues its slow crawl away from its 2018 perihelion, giving researchers a chance to watch this atmospheric engine evolve over time instead of studying it as a single frozen snapshot. So let's bring this all the way home, because the real story here doesn't end with a solved mystery. It opens up a much bigger one. Pluto's subsurface ocean question. Here's something New Horizons flagged back in 2015 that never got the attention it deserved. Its images showed a slight bulge in Pluto's crust and surprisingly light cratering in certain regions, both of which hint at ongoing geological activity, and possibly a liquid layer hiding beneath that frozen shell. The gravitational tug-of-war between Pluto and its oversized moon Charon, nearly half its size, generates tidal forces that some scientists believe could be enough to keep water liquid deep underground, insulated from the brutal cold on the surface. Combine that with what Webb just confirmed about the haze actively regulating Pluto's atmospheric heat, and you start to see a picture of a world that is anything but the dead. Frozen rock, it was written off as for decades, an atmosphere that manages its own temperature, a surface actively exchanging material with its largest moon, and possibly, hidden far beneath the ice, an ocean that's been sitting there the entire time, waiting for someone to check. That's exactly what a mission called Persephone is designed to do. Led by Carly Howitt of the Southwest Research Institute, a member of the original New Horizons science team, Persephone is currently one of 11 planetary mission concepts NASA has funded for consideration in its next decadal survey, the process that decides which major missions actually get built and launched. Unlike New Horizons, which scream past Pluto in a matter of hours, Persephone is designed as a full orbiter, capable of settling into orbit around Pluto and Charon for over 3 years, mapping the entire system in detail, tracking seasonal changes, and directly hunting for evidence of that subsurface ocean. If funded, the mission would carry 11 separate scientific instruments, cameras, spectrometers, magnetometers, radar, and more, at an estimated cost of roughly $3 billion. Here's the part that genuinely puts this whole story in perspective. If Persephone launches on schedule around 2031, the spacecraft would need approximately 27 to 28 years just to reach Pluto, arriving sometime around 2058, using a Jupiter gravity assist and radioisotope electric propulsion to make the trip. Once there, it would spend roughly 3 years in orbit, with the potential for an extended mission stretching the entire operation past 50 years total. Think about what that actually means. A child born the year this mission launches would be approaching retirement age before humanity gets its first orbital data confirming or ruling out an ocean on Pluto. This is what patient, honest science actually looks like. Projects planned not for the next headline cycle, but for the next half-century, built by scientists who understand they may not personally live to see the answer to the question they're asking. And that patience is exactly what makes Webb's 2023 discovery, formally published in Nature Astronomy in 2025, so remarkable by comparison. A prediction made in 2017 by Xi Jiang, initially treated with real skepticism by much of the planetary science community, was confirmed within roughly 6 years once the right instrument finally existed. In the world of outer solar system research, where mission timelines are routinely measured in decades, that's fast. That's science moving at a genuinely thrilling pace, precisely because Webb gave researchers a tool sensitive enough to finally test an idea that had been sitting unconfirmed for the better part of a decade. So here's where that leaves us today, in the middle of 2026. The 30-degree temperature anomaly that puzzled scientists since July 2015 has a confirmed peer-reviewed explanation. Pluto's haze, built from tholins, formed when ultraviolet light strikes methane in its thin atmosphere, actively radiates heat into space, functioning as the planet's own thermostat, a mechanism nobody fully understood until Webb's MIRI instrument caught it in the act. That same haze chemistry appears to be operating on Titan and potentially Triton, suggesting a shared physical process across multiple worlds in the outer solar system. And the tholins driving it all belong to a broader category of organic compounds that laboratory experiments have shown can produce genuine building blocks of life, amino acids and nucleobases under the right conditions, raising serious ongoing questions about how far this kind of chemistry might extend across the solar system, and whether it's happening right now on worlds we haven't even properly examined yet. None of this is a cover-up. None of this required a leaked document or a whispered confession. It's the story of a real anomaly, a bold prediction nobody believed at first, and an instrument powerful enough to finally prove that prediction right, published openly in peer-reviewed journals by scientists who put their names on every single claim. And honestly, that's a more satisfying ending than any fabricated conspiracy could ever offer, because it's real, it's still unfolding, and the next chapter is already being written. So here's my question for you. If a decade-old mystery about a tiny, frozen world 5.9 billion kilometers away just turned out to involve chemistry connected to the literal building blocks of life, what do you think Persephone is going to find when it finally gets there in 2058? A dead, frozen interior exactly as expected? Or something that changes how we think about life's chances across the entire outer solar system? Drop your prediction in the comments, because this story is going to keep developing for decades, and future Webb observations of Pluto's changing haze are already being planned right now. Subscribe and turn on notifications, because when the next batch of data comes in, you'll want to already be here to see what it reveals.